Hello, dear Dr. Burns, and to whomever watching this video, if there are any. Uh, Today I'm completing the bonus task for our homework. Let's start. With in the first subtask, we're asked to convert the given assembly instruction into the binary. So first, what do we know about this? Every assembly instruction in the binary form starts with the condition flags identifier. In this case, we see that our instruction doesn't have any. Thus, it's going to be 1110, which corresponds to the absence of any conditions. Next, we know that our add instruction is a data processing one. Um, so the binary value that corresponds to the binary to the data processing one is 00. Now for the add instruction and to other data processing instructions, next bit corresponds to the immediate value, which determines if the added value is immediate or register based. In this case, we see that it's not immediate. Thus, we'll set this to 0. Now, for the add instruction, the command identifier is 0100. Next comes the S flag, which indicates if our instruction is going to affect the NZCV condition flags or not. In this case, it's 1 because we clearly see that S in the end of the instruction initialization. Next comes our first source register, which in this case is R6. It corresponds to the value 0110. Next comes our RD or destination register, which in this case is 1001. And then comes the source. So for the source, since our immediate value identifier is 0, we're using the register-based source indication. It takes up the 12 bits of the whole instruction and consists of shifting shifting operations indicator if we have any LSL like shift L or shift right or any other shift operation. But since we don't have any, we'll set all the bits that correspond to the shifting to 0. So first 5 bits are occupied by the value by which we shift, and the second 2 bits in the source 2 part of the instruction are the type of shift operator, which we don't have, so we set it to 0. The next one is by default 0, and the very last 4 bits of the instruction are our second source register, which in this case is R5, and in a binary form it's going to be 0101. Now to make it look nicer, since we have 32 bits and 32 bits are divided in 8 bytes, each of which is 4 bits, we're gonna fix it. And here we see the binary representation of the adds R9 to the register R9, the values in R6 and R5. Now let's jump straight into the second subtask, which tells us that we need to convert this given hexadecimal value into a readable ARM32 assembly instruction, human readable. First of all, we need to convert this hexadecimal value into the binary code with the help of simple algorithm in which we take each element of the hexadecimal representation and just convert it to the 4-bit binary. So we have 1110 for E, then 1, 1001 for 9, then zeros, and then 5 at the very end. So by looking at this, what we can tell? First of all, we can tell that our whatever instruction we have, it doesn't have any conditions. Next, we see that if we take the next 2 bits of our binary instruction, we can tell that this is a memory instruction because 0, 1 corresponds to the memory instructions. So for memory instructions, the 32-bit binary instruction is distributed, like arranged in a specific way. So this 6-bit helps us to determine many things. First of all, what specific instruction we're using for loading or storing, what type of indexing, and also offsetting. The next 4 are for the first source, then we have destination, and then our second source, with the analogy with previous subtask. So let's determine first what specific instruction we have here. So this bit is labeled as L and tells us if the instruction is load or store. In this case, it's going to be store because the L is set to 0. Then let's look at this bit at a position 20, 21, 22. It's labeled as B and tells us that our instruction is going to store data byte by byte. Next, let's determine our registers. So here we see the destination one, R9. Then here is our first source, R6. And for the second source, we see the 12-bit representation of that. So to know if our storing will be in immediate value or the register based, we look at this bit. It's 1. If we complement it, we get 0, and it tells us that we have the register based storing. For the register based, we look at all this 12 bits, and from this we see that we have absolutely no shifting in our instruction, and this bit is 0 by default. So it tells us it's going to be just the register that we have at the very end, which is register R5. Now let's consider the indexing. So to determine indexing, we'll look at the label P and the label W. Here we can see at the position 24 it is 1, which is label P. and the W at the position 21 is 1. 1 and 1 correspond to the pre-indexing, which is going to look like that. Also, we have the U label at the position 23, 25, 24, 23, set to 1, which tells us that we're gonna add offset to the base. So in this form, everything is correct, and we have successfully completed the subtask. So thank you for watching. Goodbye.